이게 아니 성준이가 뭐 물어보던데 안드로이드?
네, 안드로이드
그래서 뭐 휴대폰으로 해야 된다며.
해결을 못했어요. 이거.
너 이거 안드로이드 아니?
근데 그냥 걔가 해결을 못했어요.
걔가? 이걸로 너 휴대폰 하면 될걸?
Okay, so let's start.
내가 가상 컴퓨터 알고.
So I think this is our last lecture. So today we are going to have a quick overview of what we have learned in this semester, and also we are going to have a final exam review to inform you the types of final exam questions. Okay. So I think in the past 13 lectures we have learned the basic fabrication principles and the masters in the IC fabrication, including overall the overview of the fabrication, Process Pro to all the details starting from the silicon wafers. And I think but in the end of these slides we have the fabrication Process Pro to show us all the details of the technologies that are needed in the IC fabrication. Okay, so I think all this for the final exam, I think we will cover all these lectures. Okay, but we will not go deep. So, for example, for the silicon, if showed in the title, definitely we will have the question related to the silicon wafer, and oxidation. Yes, we have, and also the dry etching. We need to understand the difference of the wet and the dry etching. We also have question cover the CVD, and yes, we have question the metallization, multi-level chips, the doping, and the back end of line technology. So all the items listed here will be covered by the final exam. Okay, so the good thing that you have sufficient time to prepare for the final exam. I think our final exam should be the last one. It should be the last one of the final exam. It's scheduled the May 29th. I think this is a Tuesday, afternoon from 4:30 p.m. So 2 hours, and the loading actually is not heavy. And room 2464. Before the exam, please check the SIS system to make sure if there's any change of the room. Different from your in-lecture quiz and different from your in-lecture quiz. The final exam will close book. So there are several tips for you to prepare. The first thing that in these slides, I add all the questions and the corresponding answers of the in-lecture quizzes. So please read and remember all these quizzes. And behind each quizzes, you need to understand it and learn the fundamental knowledge. And our final exam will also cover the questions in the lab sheet and also the lecture notes. It is closed book. You cannot use your laptop, you cannot use your mobile phone and iPad, and any other equipment. So, and the academic integrity is, I think it's the highest priority. You are not the junior students, and I believe that all of you know about it. And you need to prepare the pencils, the erasers, the rulers to join, because you need to draw the cross-section view and also the fabrication process. And if you need, to be honest, I think we do not have complex calculation, but you can bring a simple calculator. So for the content, the total variable mark would be 120. Okay, but the actual full mark is 100. So we may abandon some questions. So we will have, again, this is a closed book, so I do not want to degrade the difficulty too much. So you can abandon some questions in your final exam. And for the types, we have 4 parts. We have single choice questions. Okay. Sorry, I think here is wrong. There's no multi choices in the final exam. Sorry. I will update the slides later. So, the part 1 is a single choice questions, different from your in-lecture quizzes, which has multi choices. And part 2 is define and explain briefly the following terms. So you need to understand the terms in the IC fabrication. You need to remember. Okay, and we also have short questions, which is also very similar to in-lecture quizzes. And the last part will ask you to draw the process flow, so which need your understanding of the IC fabrication, and also you can understand the top view and the cross section. So I think in the lab report 5, most of you misunderstood the cross section report. Okay, so for the part 1, I think we are going to review the in-lecture quizzes, so you will understand what is a single choice questions. So in the following part, we can start from the part 2. Okay, and for here is also, I think we can do a dry run, right? So here I put the items here. You can think about if you still can wake up your memory or not. Okay, so now you still can check the slides, but in the final exam you need to make sure you remember the details. For example, the first one, what is electron migration? For this part, I think we did discuss this when we in the lecture for the metallization, right? And we also discussed about the method to suppress the electron migration. Okay. So it is related to the current flow. When metal carries large current density, which refers to the large current flow, the motion of electrons hitting the metal core ions and leads to the ion motions and cause the voids or the heat loss. Well, you do not need to be so professional, but at least you need to write down that, okay, under the large current flow or large current density, the atoms of the metal will move from one place to another. Right? You can make the answer simple, but must match the key point. Okay? So electron migration. The second is Burr speed. I think we discussed this many times in the lecture and also in the lecture quizzes. Right? So what is Burr speed? So it is the phenomenon in the oxidation process, right? In the local oxidation of the silicon, we need to use the nitrogen and hot mask to protect the area which you do not want to grow the silicon dioxide. So what is the Burr speed? That is the profile, right? The profile of the grown silicon dioxide between the field region and the active region in the local oxidation of the silicon. And in the part 2, you may also ask what is the locus. You need to understand the following, right? Locus is a very professional term in the IC fabrication. And definitely you can discuss about the drawbacks, the limitations, the issues coming from the fabrication. Okay? So the next, I think our part 2 will also, final exam will cover the types of mask. I think more than 50% of you, I think, answered the question in the lab report in the wrong way. So you need to understand what is the bright field mask, what is the dark field mask. The field here refers to the area outside the pattern, not the pattern itself. So the bright field mask, which refers to the type of mask where the patterned region are non-transparent. So you can see the opposite situation, right? The transparent and the non-transparent. So for the dark field mask, which means the patterned region, they are transparent, right? They are blind. So I think you need to understand the definition. And we also have discussed about types of photoresist. You need to understand the definition or difference between the negative and the positive photoresist. Okay? can give you half a minute to think about the difference. I think today we want to show you different types of the questions. We also want to wake up your memory. We're going to have more than 20 questions, so you need to make sure you can have a quick wake up of the memory. Right. For the PR, we have two types, positive and the negative. The positive PR refers to the type after reacting with the UV light, right, can be removed by the development. While the negative PR is the opposite, right, after reaction with the UV light can be remained on the wafer after the development. So here, unexposed part will be dissolved or can be removed during the development, right? And the exposed part remains. So all these things you need to remember. Well, you do not need to be professional again. You can use your own words, but make sure you remember the key point. Okay, so then what is the IE? So these terms you need to remember: reactive, inductive, etching, right? So reactive ion etching, an etching technology which use the chemical reaction ions in plasma to bombard the target material and react with it. Okay, so in addition to the IE, we also have the ICP, right? Here, this I, the ion. This I refers to the inductive, okay, inductive coupled plasma. And we also discussed about the two-step diffusion. So when you look at the two-step diffusion, the diffusion part, so you should wake up your memory that we discussed during the ion implantation and ion diffusion. And then you need to wake up your memory to understand the difference between the diffusion and the implantation. Right? Actually, implantation also has several steps. For the diffusion, the reason why we have two-step diffusion because we want to control the amount of dopants, which we have covered in the lecture and also in the lecture quizzes. So, what is two-step diffusion? We have the pre-deposition to introduce a certain amount of dopant, right, to the wafer, to the top surface. And then we have the second step, we call it drive-in, to diffuse a certain amount of dopant into the wafer. Okay, so here is just show you some examples, and also let you understand the difficulty level of the final exam. So for the PECVD, you need to understand the full name of PECVD. In addition to the PECVD, we also have the LPCVD. So what is PECVD? Think about it. Okay. Try to wake up your memory. You have to try now, then you will understand the effort you need to put on the final exam. Okay. So here you can see, then you need to wake up your memory for the CVD, right? And the CVD is for the material glowing. So for the material glowing, we have different types in addition to the oxidation. For here, you need to understand the difference between oxidation and CVD. Right? Oxidation needs to consume the silicon, while CVD is going to consume the gases without consuming the substrate. So then we have different types under different pressure and temperature. So the PECVD is for the low temperature, below 350 degrees C. Then how to enhance the reaction? We use plasma. So the PE stands for the plasma enhanced CVD. Right? We also have a LPCVD, the low pressure CVD, based on the high temperature. When the pressure is low, we need the high temperature to activate, to give the energy, contribute to the reaction. Right, so then you need to write down the full name, plasma-enhanced chemical vapor deposition. And we also have discussed about RTA, the rapid thermal annealing. So you also need to understand the full name and understand the purpose of this kind of equipment. Okay, so the city side. Think about it. What is the city side? You can wake up your memory around the metallization. At two weeks we discussed about the city side. If you cannot wake up your memory, then please read the slides before the final exam. So it is a compound of silicon and a metal formed at a high temperature annealing. So it helps to reduce the source and drum and the gate resistance. Okay, so and also it can help us to suppress some other negative effects, including the migration. Okay, set aside. I think we discussed this in the lecture for the metallization. Okay, so what is the low K ITD? So in the IC fabrication, in the IC devices, the K, you need to understand what is the K. I think we discussed this. The K stands for the dielectrical constant. So low K and high K. So what is the dielectrical constant? I think you must have learned in your previous physical courses. It is used to characterize or to help you to understand the capability in storing the energy. So in other words, the dielectrical constant can help you to calculate the capacitance of the certain structure. Right? So if we have a capacitor, then top and bottom electrons, and with the material inside. So the material between the two metals will help you to determine the capacitance of this capacitor. The same situation in IC fabrication, right? Or in the IC transistor devices. In the transistor, we have multiple electrons, right, to form the source, the drum, and the gate terminals. And these electrons can form the capacitor. Then to give the capacitance, working as the parasitic branches to the equivalent circuit. So if we can decrease the dielectrical constant of the capacitor, we can decrease the capacitance, and then to decrease the parasitic effect. Okay? So here, the low dielectrical constant in the interlevel dielectric. Okay, what is the interlevel dielectric? In addition to the transistor, we also need to build multi-layers above the transistor to build the interconnections. And these interconnections, multi-layers, we have the metal. I think we have seen the pictures. This metal will also form the capacitor, right? So to decrease the value of the capacitance, we need to make sure that this interlevel dielectric, they feature the low dielectric constant. This can help us to reduce the interlayer capacitance. Okay? So for this part, I think you can get it from the multi-level chips. So then, what is STL? This is, I think we covered in the last quiz, right? About the shallow trench isolation. So you need to understand the different technologies that we use in the isolation. In addition to the STI, we also have SOI, right? You need to understand what is SOI. Nowadays, the IC industry, they are using SOI. The ultra thin silicon film on the silicon dioxide. Right? This can help us to get the good isolation between adjacent transistors. Okay, so this is the part 2, and so you can see that all these terms, they're covered by the topics listed here. So please go through the slides before the final exam. I think 1 week should be sufficient for you to read all the slides. Okay, I think 1 week should be sufficient. 2 weeks, after 2 weeks, you may forgot what you learned in the first day. Okay, so 1 week should be sufficient. Okay, so
is that part 2 is that definition questions?
yes, the definition
Just
questions.
give me a word to explain.
Yes, correct. To be honest, there are not too many terms there. I think there are not too many terms. We have how many lectures? 13 lectures, right? Each lecture maybe 2 or 3 terms. And you can do the summary. It's very important to remember these terms after learning the IC application. Otherwise, in the communication, there are too many words without these terms.
We only have to like briefly describe the function
Yes.
for 1 or 2 sentences.
Yes, or you can give, if it is so hard for you to, to explain the full name, for example, STL, you know it is for the isolation, but you cannot remember what is the standing of the S. Then you can say, okay, this is isolation method is used to use the trench or using the action method to create isolation between tracing traces. You also can get the point. Okay.
Is this like the answers written in the PowerPoint is enough for us to write in the real exam?
Okay, second.
So like, is this like number of sentences or this line, this written answers are it fine for us to just write in exam just to get a
it's
full
fine.
mark?
If you can provide related information, so you can get partial point. You can get partial point. Okay, for example, if you forget the shallow trench, then you can say, okay, this is a compact and effective isolation technologies. Then you can get also point. Okay. Okay, so the part 3 is based on the short questions, right? So it's not to explain the terms, but to answer some questions. And for example, the traditional question is to understand the docking type and orientation of the top surface. I think we also have covered this, right? So give you half minute to wake up your memory. I guess none of you can remember. We in the lecture we have the table. So before the final exam, you need to remember that table. For example, the first one. The first one has the 2 flags, right? The 2 flags with the orientation difference 19 degrees. So this refers to the P type. Okay, P type and 100. 100 orientation. So for the P type, there are two different orientations that we have learned. One is 100, another is 111. Okay. So the third one is also the P type. Orientation is 111. So for the P type, there are 2 different locations of the minor flags. Without the flag, that will be 111. With the minor flag that is 90 degrees to the major flag will be 100. Okay, so then the second one is N type, right? The N type, the orientation is 45 degrees, so it is 111. So the N type, the 100 orientation, the angle difference will be 180. The minor flag to the top of the major flag. Okay, so yes, we have the table. We have the table. So you just need to remember the table, and you'll be fine. Or there's another way to remember this. For the 100, right, the difference, the orientation difference between minor and major should be less than 90, less than 45. Right, this is 45, this is 0. We can treat this as an overlap between the major and minor flange. Right, for the 100, the orientation difference should be larger or equal to the 90 degree. Right. And the orientation difference larger refers to the n type. So let me repeat, okay? The difference between n type and the p type is that the n type features a larger orientation difference compared to the p type. And the difference between 100 and the difference between 111 and the 100 is the value of the orientation difference. The 100 also features a larger orientation difference compared to the 111. So this way we also can remember these 4 different types. Okay? So because in the industry they have so many different types of wafers, the equipment engineers need to identify all these different types of wafers. So they are using the location of the major and the minor flaps to identify the orientation and loading type. Okay, so for example, the short question, these 3 methods to deposit metal on the wafer surface. Okay, so for this part, you can check the method in the metallization. So how many we have? We have sputter, right? We have evaporation, and we also have electroplating. Okay, so electroplating is very common for the upper layers where it needs a very thick metal. You also need to understand the difference between the sputtering, the evaporation, and electroplating. The sputtering and evaporation can be useful for the metal thickness less than 500 nanometer. For the thicker one, you need electroplating. Okay, please go back to check the details of the slides. And you need to also understand what is epitaxy. Right? I think it's related to the CVD. We discussed about epitaxy in discussing the CVD technologies. So there is a difference between epitaxy and non-epitaxy. Epitaxy refers to growing the single crystal material on the single crystal substrate. Okay, I think we have a definition in the slides. Okay, so the next example, please draw the top view. Oh, I think all the slides I have uploaded to the cameras. Right, so after the lecture, you still can see the details, and based on these questions, go back to check the slides. So please draw the top view of 100 orientation and type. I think we have discussed that the N-type feature the large orientation, right? And 100 also feature the larger. Then the orientation difference would be 180. So right. Here is I understand the drawing sometimes is hard, so it's better for you to do the notation. This is the major flat, and this is the minor flat. Yeah. Yes, we have the picture. Okay, so you need to label. Okay, you need to label the location and the size of the plant. So should the air pressure in the yellow room? Okay, so this question is related to the clean room. Definitely will be covered in the final exam. Should the air pressure in the yellow room be higher or lower than that of the outside? So this question is related to the to the design of the clean room related to the air pressure and related to the airflow. So the yellow room means that we also have discussed different levels, right? What is the function of yellow room? Why do we need yellow room? I think you have visited the phase 2. You can see that in the phase 2, the yellow room is inside of the white room. And we also have discussed why we need the yellow room. Right? It's photolithography. It can help us to protect the PR. In other words, for the PR, before the exposure, it cannot be opened in the white room. It will have the reaction. The white light will have a reaction with the PR. So the yellow room is photolithography, and it features a higher cleanness level. So in our phase 2, the yellow room is 100 level, while the white room is 1000 level. And outside is the white room, that is a gunning room for you to change the clothes. The level is 10,000. Okay. So then let's return back to the question. Should the air pressure in the yellow room be higher or lower than that of the outside? Should be higher, right? Because we want the air flow from the high level clean room to the lower level clean room. So we need a higher pressure in the high level, the yellow room, to make sure that the contamination cannot flow from the white room to the yellow room. Straightforward. So the next question, what is the origin of the interface state between the silicon and the silicon dioxide, and how to reduce the density of it? Think about it. I think we discussed this in the oxidation. We also have discussed a method to fix or to rearrange the interface between the silicon and the silicon dioxide. So it is due to the incompatible atom arrangement at the interface. Like some covalent bonds are incomplete. So, and we also have discussed about the annealing, right? The high temperature annealing. So for this part, I think you can go back to check the slides for the CVD. Check the slide of CVD. We also do the comparison with the CVD and oxidation. For oxidation, the quality, the interface quality is better than the CVD. And we also discussed the method to clear the interface quality. Okay, so the next, what are the reasons for using a dry, wet, dry circle in the field oxide reaction? Think about it. I think we discussed about the dry, wet circle. So then think about what is the dry, wet, dry circle. Okay, so I think in the lecture we discussed about the difference between the dry and wet oxidation, right? So the dry oxidation can give us a good quality, not only the interface between the silicon dioxide and silicon, but also the top surface. Because the dry oxidation is slower, right? And in the lecture we show you the picture to do the comparison between the top surface roughness with a VS relationship of the growing rate. So the lower growing rate can give you better or smaller surface roughness. So that's the reason why at the beginning and at the end we have the dry oxidation. The dry oxidation can give us, let me repeat, the dry oxidation can give us good quality between the silicon and the silicon dioxide. And we end at the dry oxidation to improve the surface roughness. But the dry oxidation, the oxidation speed is too slow. So that's the reason why in the middle, right, we need the wet oxidation to help us to short the process time. Okay, so you can go back to the slides to see the details. Okay, we also have questions related to your fabrication. I think some of you have misunderstood this ruler in the lab report. So in the lab part, we used the I-lam for the lithography. And I think we discussed about the different lines, right? The G line, the I line, the different wavelengths under the UV light. So what is the wavelength of the I line? Okay, I think this is a little bit hard question. If you do not do many times of lithography, you may not remember the wavelengths. Okay, so that's the reason why. Okay, so because some of you are late, so let me repeat the policy. Okay, so the total available mark will be 120, but based on my experiment, no one can reach the 120. So the actual full mark. Okay, yeah, because I do not expect you to remember all the details. So the actual full mark is 100. Okay.
So if I get maybe 101, then I get 100, right?
You'll get 100. Yes.
So actually, I only
No,
I don't need
no
to answer
burners.
everything.
Yes, no burners. So that's the reason why I said the 1 week preparation should be sufficient. Maybe over 1 week we can get 110 or 120 is possible. Okay.
So it's out of 100.
Yes. You can control, right? After you can make sure you get 100, then you can leave.
시험 보는 거 같은데.
Okay. Yeah. So because I know that some questions it's a little bit hard. It's a little bit hard, and I do not expect you to remember all the details. Okay. So what is the wavelength of I line?
No multiple choice or is there any multiple choices?
No multiple choices. So I'm going to update the slide. I think I write down the wrong policy here. Okay, single choice, no multiple choice. Okay, so it is 365 nanometer, and this is for the misalignment check, but they are not used for the alignment. In the lab report, some of you say that okay, these are used for the alignment. No, we have the close marker, okay, during the alignment to help you do the alignment during the exposure, and these rulers are used after the development to check the misalignment. And I think in the lecture I also have explained how to read the misalignment. So these two rulers, vertical direction and lateral direction, can help us to read the misalignment in two directions, right? So we have the number here, and if the rectangular of the certain value, there's a perfect aligned, so then the misalignment will be that value. For example, here is 4. Sorry, let me check which part. Okay, this is 2. Okay, and this is 0. It seems that these two they're aligned in the middle. So then the misalignment would be 1 micrometer. And for here, well, it's hard to say. Well, I think here it's hard to read the misalignment. This is 0, slight misalignment, right? And here we can have a misalignment larger than this one. So which means, and here is 2. So we can guess a rough misalignment here is like 0.5 micrometer in the vertical direction. Okay. I think, let me check. I think I have a good example to you. Maybe the last week we discussed one part. Let me check. Sorry, let me. Okay, so I think we discussed this last time, and we are also going to have the similar questions in your final exam. So I give you 3 or several cases. So from the cases, you need to know how to read out the misalignment. So the misalignment reading is based on the overlapping. For example, here we have the overlapping under the 0, so which means the vertical misalignment is 0. Right? We can read it directly. And here, the same as the vertical one, right? We get the perfect overlapping under the 0. There are no misalignment. While for the case 2, for the lateral one, we can check which lines or which rectangular blocks that achieve the perfect alignment. We think that's this one, right? This one achieves almost perfect overlapping. And under it, the value is 4, the number is 4. So the lateral misalignment is 4 micrometers. Right? For here, it's still 0. For the right one, we also can read with it, right? Try to find the perfect overlapping. So here it seems that's this one, vertical one. So the misalignment is 6. For the lateral one, so it seems that it's this one. Then the misalignment is 1 micrometer. This 2 is 0, then this is 1. Okay, so we will have the similar questions in the final exam. Okay, so the next short question. The then 2 diffusion mechanisms which are possible for open diffusion in the center, and which one is taking place in the phosphorus diffusion. So yeah, we have two types, right? This is also the hard question. I expect maybe 10% of students can answer this. Again, in the final exam, you will not see the same question we discussed here. Okay, you will not see the same question, but the same type. For example, we have other questions related to the diffusion mechanisms. But do not worry. I think the grading, the history, okay, the grading of 4, 5, 20 in the history is pretty good. So do not need to worry about it too much. Okay, so comparing the mass transport limit and the reaction limit, which one is beneficial for good step coverage? Why? So I think it's related to the challenges we meet during the CVD, silicon dioxide deposition. You can go back to see the slides. That's when we show the step coverage. And we also discussed about the limit, the limiting factors. So which one is beneficial for the good step coverage? The reaction limit. Okay, the reaction limit is beneficial for the good step coverage. And the reason is that so that's a step. So its step will prevent the mass transfer along the surface. So in this case, the transport of the atom will be prevented, and the chemical reaction will not be prevented. So the chemical reaction is not dependent on the location. Okay, so let's see the option. The reaction limit is beneficial for the full step coverage because the chemical reaction is not spatial dependent. Okay, so the next, what is the reason for tilting the wafer at 77 degrees when the implantation is performed? Okay, I think we discussed this two times. One is the intellectual quizzes, another is lab report. It's for the channel effect. Avoid the channeling effect. So what is the channel stop implant? What is the purpose of this kind of implantation? I think we discussed this in the isolation part, right? To guarantee the isolation between the transistors and between the dopant areas. So the channel stop implant, it's a certain field regions before the silicon dioxide formation. I think you have seen that picture in our, I think in the lecture 12. Okay, so show here. It's going to increase the field threshold voltage. Okay, I think this is the lecture 12. Okay, the next one, the gas oxide thickness must be controlled in a very precise manner. So what problem it may cause if the gas oxide is too thin? Think about it. This is also the hard question. Need your knowledge from 3500. So here's my suggestion. Okay, in the final exam, if you met the question you cannot answer, just give it up. On to the next one. So the gas oxide thickness is related to the threshold voltage. Okay, I think what is the threshold voltage? We also have discussed, and you also have extracted from the last lab report. The current lab report we are going to submit this Friday, right? This Friday morning. So if the gas oxide is too thick, the threshold voltage will be very high, right? And then this will have the situation or phenomenon in the leakage, the current leakage. And also, if there's a sudden large power or voltage, that will be the gas breakdown. Okay, so what happens it may cause if the gas oxide is too thin, the threshold voltage will be too small, and the gas leakage current will be too large. Okay, the current will be large, and then the gas breakdown will be low. Okay, so you can see that all these questions, the questions cover most of topics that we have discussed. Please read the slides. Okay, so after the section, the part 3, Okay, the short questions. The next one will based on some fabrication process flow related to the overview of the MOSFET. So let's see this question. Give you 1 minute to understand it. This also needs some basic knowledge from 3500. I think at the beginning, in the first 2 or 3 weeks, we discussed about the fabrication process flow of the diodes, the NMOS, the PMOS. Think about it. The last part of the final exam, before joining the process flow, you can have a try. So give you another 1 minute to have a try. Okay, so for here, I think to answer this question, you need the basic knowledge from 3500. You need to understand what is an unwell Schottky diode, right? It's a type of Schottky diode that is integrated into a standard CMOS. What is CMOS? Well, the complemental metal oxide semiconductor. So by CMOS process. So and the unwell Schottky diode uses the existing unwell region of the semiconductor substrate. Okay, so you need to have the unwell. And for the structure of the fabrication of the unwell Schottky diode, actually you can refer to the NMOS and CMOS. So in a typical CMOS process, unwell is a region where the N-type dopant, like the phosphorus, diffused into this is unwell, right? What is unwell? Unwell is a region where the N-type dopant is diffused into a P-type substrate. So this is a P-type. So you need to have a P-type substrate first, and then diffuse the N-type dopant to form the unwell, right? So you can get information from the PMOS. That's the reason why in this question we put the PMOS and NMOS cross-section view here. And the unwell Schottky diode uses this unwell as one of the electrons. Because it is not the MOS structure, right? It's a 2-terminal structure, not a 3-terminal structure. So the key component of the Schottky diode is the metal semiconductor junction formed between a metal and the semiconductor unwell. Okay, so that is the diode. So again, the unwell can work as one of the electrons. So then you just need another electrons and a semiconductor region to form the junction. You can fabricate the diode. Okay, so then you need to know how to, so we also put the hint here. The first, because the question here is asked you to draw, refer to the PMOS and NMOS to draw the fabrication process flow for the unwell Schottky diode. So then you need to understand before joining the fabrication process flow, you need to understand the final structure of the N-ware Schottky diode. Okay, so this is the Schottky diode. This is N-ware. So, and also two terminals. As the understanding of the N-ware Schottky diode, we know that the N-ware were connected to the one terminal, right? That's the reason why there's only one junction. Okay, so we can choose this one as a terminal connected to the N-ware. And we already have the P substrate here. So we create the N-ware. So we create the N-ware. Okay, this is N-ware. You can learn from the PMOS. And this N-ware connect with one terminal. So then the diode. What is diode? Simple junction, right? So we need to create a junction between these two electrons. This is for the N-ware, and this is for the p-type region, which means we just to create another region here. Okay, so then the question, this should be the p-type or the n-type. I think you need to think about it. Because it's different from the most. Okay, it's different from the most. So maybe some of you are already seeing the slides, right? So it should be the N plus, okay, which is different from the most. Okay, so for here, so you can see that the doping ratio is actually a relative value. Okay, it's a relative value. So for the N-ware Schottky diode, okay, it uses a different doping level to form the junction, to get the turn on and turn off in different current flow direction. Okay, so I can tell you the final exams question will be easier than this one. Okay, will be easier than this one because this needs some knowledge from 3500. Okay, so let's see the question. Sorry, let's see the answer, right? So the first step, you need to understand the structure of the Schottky diode. In the N-ware and among the N-ware, we need another dot region with a different density, which is N plus, right? To form the junction, then the two terminals can work as a diode. And the Schottky diode is also different from the other types of diode, right? It has the stop region. That's the reason why it needs an N plus inside the N-ware, not the P region in the N-ware. Okay, so after getting this structure, so the next step you are going to draw the fabrication process flow, which we have discussed in the previous lectures. So in this part, the first, you need to draw the substrate, which is the, Let me draw it. So the first step, you need to draw the cross-section view, which is the P-type subject, right? So then the next step, you need to draw the cross-section view, say that, okay, you create the n-ware, right? And then the next step, in the n-ware, you create the n-positive region. And then you need to do, and then you need to define the top electron, okay? So this is a rough idea, but how then you need to fill in the substep, for example, from the P-type subject, how to get the n-ware. This is based on diffusion, right? Diffusion or implantation. Then we need to have the mask here to help us to protect the undocked region. How to do that? We need the silicon dioxide, right? The same here. Sure, from the n-ware, we need to build another n-plus region. Then we need also the mask here. Okay, so for the fabrication process flow, my suggestion is that first finalize the structure. Okay, so then put them in different major steps. And between major steps, you need to add in the minor steps, the sub-steps, to show the process. So let's see. Let's see the process. Okay. So draw the process flows. First step, you need to get the mask and the mask for the diffusion. You need to show the fabrication process. Sorry, see, this is another question, right?
Yeah.
Another question. Okay, so I did not put the.
Draw in like this vertical.